So good morning everyone. Welcome again to Midas Metro webinar series. And today is the third and the final session in the Metro webinar series. And the topic of discussion for today will be live modeling and analysis of real structure interaction in Midas 7. So the major topics that we will be covering in today's webinar will be majorly related to the program. So till now, whatever we have discussed is mostly the case studies, the theory, but today we'll be seeing the other front of the engineering, that is the program. That is a tool that we use for simulating the practical situations. So the topics that we'll be covering in today's webinar will mostly include the recap of previous webinars. So whatever we discussed in the last two sessions of Midas webinar series for metros, we'll be just reviewing, we'll be just going through those little basics, and then I will be showing you one GAD of the bridge, that is the general arrangement detail of a bridge, that we'll be modeling today and analyzing it. And then we'll be doing a live modeling using a rail track analysis module. Okay, so I will be showing you the basics also. I mean, how to go about modeling, what are the basic features that we need, what are the basic things that we need to keep in mind before we start with the modeling. And then I will be showing you some of the results for Midas webinar series. Okay, so, and finally I'll be showing you the summary, the related summary of all the things that we have covered up till now. Okay, so these are the basic contents of the webinar today that we'll be discussing. Okay, so after this, so we will go through what we have discussed in the previous webinars up till now. So in the first webinar, we discussed the use of mass transportation systems. So what are the general concerns regarding the mass transportation systems? Like, why do we need mass transportation systems? I mean, what are the different types of mass transportation solutions like metro, monorails, and BRTS, local railway transportation. Similarly, after that, we discussed the use of metro transportation systems. So why is metro being used a lot? Why is metro coming as a boom in the engineering industry? And what are the different concerns relating to metro transportations, like congestion, difficulty in construction, time of construction, the congestion of traffic, so all these things. So after that, we discussed in metro transportation system only the balanced cantilever bridge method of construction using Midas 7. We also discussed for monorails the integral bridge method of construction. And after that, I gave a little basic about rail structure interaction using Midas 7. And also then I showed you some metro project applications regarding the metro projects of Chennai, metro projects of Delhi, metro projects of Hyderabad, and using Midas 7, whatever the solution, whatever the applications that have been done, whatever the bridges that have been done using Midas 7, I showed you some of the applications. After that, in the second webinar, Mr. Akshay Vahal and Mr. Nitin Mittal gave you an introduction to rail structure interaction. So they discussed about the continuous welded rails, how it is a necessary evil. Okay, so why we need a continuous welded rails and what are the disadvantages regarding a continuous welded rails, and because of that, why we need rail structure interaction. They also discussed the bilinear stiffness properties of connections that we need to give. They also discussed the separate and complete analysis of RSI. So separate analysis comprising of the thermal, horizontal and vertical stresses being calculated separately and then summate, and then we do a summation of all those things together. And in complete analysis, we do a staged analysis, if you remember. And then we did the axial stresses which are generated. They also discuss about the axial stresses generated in rails due to thermal braking or acceleration and train vertical loads. After that, they presented a case study on rail structure interaction using Midas Civil. So they did a case study on airport metro express line, which was done by L&T ECC itself in Midas Civil. They also did one case study on Hyderabad metro using Midas Civil. So the overall conclusion of second webinar was to show you that how an engineer has to go about rail structure interaction, what all things he needs to consider in his mind to start with the rail structure interaction, and how some of the professionals in the field have implemented RSI module of Midas Civil in their solutions. Okay, so in today's webinar, what we'll be covering is a typical bridge of typical metro bridge, which generally looks like this. So I've considered a 5-span bridge. So if you start modeling of such a kind of bridge, what you basically need is that you have to construct all these nodes. First, you have to model all these nodes, right? And then we have to model elements in between the nodes. So I can model elements in between nodes. So like this. Now, when we do these things, it takes a lot of time, right? So we create one node one by one, then elements. It will take a lot of time. Then additionally, we are also giving tapering. Okay. So after that, when the tapering is done, I mean it takes a lot of time to create such a bridge. So in order to reduce time, we have some specific wizards. So for such a kind of bridge, also we have free cantilever method wizard. Similarly, we have the full staging method wizard. So such a kind of bridge is also done using wizards. But if you see here closely, we haven't modeled the rails here. This is a simple bridge, but we haven't modeled the rails here. Also, we haven't modeled the embankments at both ends, right? So what we'll do using rail structure interaction is that we'll model the rails also over the bridge, and also there will be some embankment at both ends of the bridge. Okay, so we'll be doing this thing. Okay, so we'll be modeling the embankments at both ends, and then a rail will come throughout the bridge over the deck and the embankment, and then we'll be modeling the connection in between the rail and the embankment and rail and the deck. So you can understand the difficulty yourself, that it will take a long time, because first we have to model the bridge. The bridge itself will take some time. Then we have to model the embankment, and then we have to model the rails, and after that we also have to give the connections. And to connections, we have to give different stiffness properties as per the bilinear stiffness data that we have. So for the ballast bed, we will have different stiffness data. For the concrete bed, we will have different stiffness data. And even after that, when the train loading is coming over a portion of bridge, suppose the train loading is coming from here to here. So underneath this region, there will be some different stiffness coming in the connections. So we have to consider that stiffness also. So overall, the time, it takes a lot of time. If you do a bridge like this using manually, I mean starting from the very nodes and then creating elements, it might take around 2 to 3 days or more to complete the full bridge. Okay. So this is the cross section. So at supports we are having around 6.7 meters depth section. This is a single PSC cell box section, and it is being tapered parabolically to a 2.4 meters section. Okay, so we have a tapering also, and then these are the bilinear stiffness data. I hope you already understand all these things. I don't need to go through, but still, to refresh your mind, I will just explain a little that the bilinear stiffness data we require because for unloaded conditions, when only thermal stresses are there over the bridge, there will be some different stiffness coming inside the connections. Okay, so what we do is that we give multilinear elastic links. So in multilinear elastic links, we feed in the stiffness data according to the loading that is there. So if only temperature loading is there, we give the unloaded condition stiffness, and if only vertical loading is there or train loading is there, or I mean acceleration or braking loading, then we give the loading condition stiffness. Okay, so we give two kinds of stiffness. Also, we need to give some lateral limited displacement. That is, what is the limited displacement defined for a ballast bed? What is the limit of what is the lateral limited displacement defined for a concrete bed? Okay, so in a way, we have to define all these properties to the multilinear elastic link. Okay, so we need to give some properties. So these properties that are given in the slide is according to the UIC code. So the UIC code mentions that for a ballast bed for an unloaded conditions, we give a 20 kilonewton per meter stiffness, and for the loaded condition, we give 60 kilonewton per meter stiffness. Similarly, for concrete bed, for unloaded condition, we are giving 40 kilonewton per meter, and for loaded, when the train load is coming over a portion of the bridge, we change it to 60 kilonewton per meter. Okay, these are the loadings that will be applied over the rails. Okay, so temperature load for will be given as 25 degrees Celsius for the deck and 50 degrees Celsius for the rails. Similarly, similar to the L&T ECC problem, we are again taking the same train vertical load, that is as per the number of wheels for each car. We are having 4 wheels for each car, each transmitting a weight of 170 kilonewton, and length of each car being 25 meters. Then the vertical load will be, as per the calculation, it will come around 27.2 kilonewton per meter, which will be over a maximum length of 200 meters. To just inform you a little bit, for the UIC code, we have different kind of train vertical loading. So if you want to do according to UIC code, you can give according to the UIC code also. Also, for braking or acceleration loading, we usually give 18% of the vertical loading. So it comes around 4.9 kilonewton per meter. Also, as stated by in the last webinar, there will be 2 tracks that will be coming. So one track, the train will be moving from left to right. Another track, the train will be moving from right to left. Okay, so we'll be defining the positions. We'll be defining the movement of the train also. Now we come to the live modeling portion. So what are the steps that we'll be following? So the major steps that will be there is we'll be talking about the rail track analysis wizard here. So we have seen that what kind of model we are going to prepare. We have in our mind that kind of model I'm going to prepare now, and it might take some time if I do it manually. So why not take the use of a wizard? Okay, so it does not mean that the wizard, if the wizard is not there, you cannot do it. Of course, you can do rail track analysis by manually also. So you need to create the full bridge, you need to create the rails, then you need to give the multilinear elastic links yourself and then for each multilinear elastic link you have to change the stiffness properties yourself and give it according to the loading and unloading conditions. So it might take some time from your end. So why not take the help of a wizard? So in the rail track analysis wizard, we'll be providing the general layout. So the general layout will be covering the bridge material and section property, and then we'll be covering the span length, what is the geometric alignment of the bridge, okay, and then we'll be giving some rail material and section properties, and we'll be specifying the number of tracks for train loading and eccentricities of the rail from the deck, what is the eccentricity. Also we'll be specifying the boundary conditions and bilinear stiffness data, okay, and we will be considering some ballast and concrete bed stiffness data and stiffness properties for bearings and constraints for the piers, okay. And also we'll be covering loading, specified temperature, we'll be specifying temperature, braking or acceleration, and train vertical loading, okay? And we'll specify the moving load positions after that. And finally we'll be doing one post processing, that is we'll check the axial stresses generated in the rail zero temperature and train loadings, and also we'll check results for complete stage analysis and separate analysis both. Okay, so we'll start with the Midas civil model. So this is the basic interface for Midas civil. Okay, and I will just start by clicking on the Midas civil icon, and second. Click on new project. So this is the ribbon menu that Midas Civil is having. So from this ribbon menu you can access all the options relating to modeling, analysis, and boundary condition properties. One of the very basic thing of Midas Civil is that it is very easy to understand. So whatever be the situation, whatever be the bridge, whatever be the type of modeling that you are doing, everything will follow the same left to right order. So first you can use the wizards for the modeling, then you can, if you want to change anything, you can go to nodal element, then if you want to change the properties, you can go to properties, then if you want to give some boundary condition, you can go to boundaries, then loadings, analysis, and finally results, and then design. So everything will follow from left to right. The holds correct for each and every option. So even if you are giving tendon pre-stressing, even if you are applying moving load analysis, we can just follow this simple rule. Okay. So currently I will just discuss the rail track analysis module. So for rail track analysis module wizard, we have to go to structure. So we have all the wizards in this tab. So you can just check here, all the wizards are here. So if you want to go for, suppose, a balanced cantilever bridge, you can go to FCM wizard. Second. Sorry for the interruption. Okay, so this way you can just access all the wizards. So this is the balanced cantilever wizard. So you can directly start by modeling in this. Okay, so you can start by modeling your balanced cantilever bridge, and then you can give your embankment and stiffness properties. So this is one way. Okay. Similarly, we have FSM wizard, FSM for FSM bridge. So full staging bridge, we have a different wizard for full staging bridge. Okay. So for rail track analysis, we have a separate module. This is the rail track analysis model. So this is a separate module in Midas Civil. So what it does, I will just explain. So we'll go to the rail track analysis model. So this is the first menu for the rail track analysis model, and this is the layout menu. So in this, we'll first define the bridge material. So we haven't defined any material properties or section properties yet. So what we can do is that we can directly go to the material properties and add a material property. But if we have already done a project similar to it, so we can directly import a material property from another file. So I can just import a material property from here. Okay, so I can choose a material property. So we have chosen a bridge material property. Similarly, for embankment length, I can give here as 300 meters. Suppose I'm considering 300 meters embankment on both sides. Okay, so again, to refresh your mind, what we are doing is that we will consider an embankment at first, and from here my bridge will start, and then at the end again I am considering the embankment. So in between there are 3 piers like this. Okay, so this will be the model. 4 piers, yeah. Okay, so this will be the model that we will be generating. So we'll consider an embankment of 300 meters. In the deck information, I can enter the span lengths. So we have the first span for 85 meters. Then we are considering 3 spans of 130 meters. If you remember the GAD I showed you. And then at the end, we are considering another 85 meter span. Okay. So you can have different material properties for different span also. For that, you can just go to advanced, and here you can choose the deck length and give a different material property as your wish. Okay, so you can have different material properties for different decks. Also, the span type we have to define. So if we are having a span type in which the first bearing is roller and fixed, and both the other bearings are roller, you can go for type 1. Similarly, we have type 2, we have type 3 for simply supported, and type 4 again. If you have a bridge which is having some other kind of bearings, okay, suppose it is just fixed, it is fixed in all the intermediate position, and we are giving rollers at both ends, then you can go for an advanced option. Okay, so in here you can choose the number of span for each deck. So I can choose 1 for each deck like this. Okay, and I can choose the roller condition. So I can choose that deck 1 first support is roller and deck 5 last support is roller. So in this way I can consider any kind of span information, any kind of support condition to assign it to the spans. Okay, for simplicity I'm just taking type 3 now, simply supported. For rail material data, either you can enter again the rail material data, or I can choose from the rail material data. Number of tracks, at max we can define only 2 up till now. Okay, so you can either define 1 track or 2 tracks. This additional check is required when we are having some extra axial stresses. So in that case, we are having 2 types of additional check. One is zero lateral resistance, and another is rail expansion joints. So when an additional stress it exceeds a certain level, ZLR, that is zero lateral resistance, can be installed to reduce that additional stress. Okay. Similarly, when ZLR is also not able to reduce the additional stress, then we can go for rail expansion joints. So we can define both these things. Okay. So we can just define the ZLR and rail expansion joint. After we have analyzed the model, if we find there are some extra stresses coming, then we can define it according to our conditions. Okay. So this is the basic layout of the bridge that we have done. So after that we come to the next tab, that is the sections tab. So in the sections tab we'll be giving the section database. I mean what is the sections that section that we are considering. So for now I'm importing the section from another Midas file. So for importing again, I can go back to this button with 3 dots and I can click on import, or we can either add and go to PSC section and make our PSC section here and then add the sections. But for now I am importing the section. So I can import a limited number of sections like this. Okay. So after importing, I choose the bridge section. So here you can find different decks. So this is deck 1, for deck 2, for deck 3 we will have different sections. For deck 4 how we'll have the sections. Okay, so I will choose tapered option here. If you remember from the slides, I will just show you the slides here. So if you remember, we were having a tapering from the mid span section to support section, from support to mid again. Okay, so we are having some tapering here. So in this direction, some parabolic tapering we are having, some quadratic tapering. Okay, so this way we have to consider tapering in the decks also. So to consider that, okay, so to consider that, what we have to do is that we'll give a tapered section assignment. Okay, and then we can choose from start. From start we are tapering. We are starting the tapering from the start itself. So I'm giving a location of 0 meters, and we are giving span section. Okay. And from start to 82 meters, the first span is of 85 meters, but for the 6 meters over the piers, we are considering only support section. So we need to consider the tapering only up to 82 meters. So I consider 82 meters from the start itself, and I give support here. Okay. And now if I go to tapered option, I can choose quadratic here and INJ. So INJ basically means is that what it means is that if I want to taper it from the ith end or the jth end, so basically to refresh your mind, what happens is that if I construct an element from here, from one end to other end, so this will become my ith end and this will become my jth end. Okay, so this is the way that we are tapering, and the tapering is something like this that we are considering. So we have to consider from I to j. Okay. So we can modify, we can click on modify, we can click on OK, and then OK. So this is for deck 1. I can copy this this particular deck data to another deck. Suppose deck 5 I am copying it. Okay, so automatically all the data from deck 1 will be copied to deck 5. So if I just a second. So if I go here, it is automatically copied. Okay, but for the deck 5 we cannot have the similar tapering because the tapering is opposite now, right? So I need to consider different kind of tapering here. So I need to consider 3 meters, and it is tapering. The tapering is starting from support section. So I will click on modify 3 meters again because we are having support section over the piers. Okay, for the deck 5 I am taking. Okay, and from the start at 85 meters I'll be having span again. Let's save this model file somewhere. Okay, so after that I will just click tapered option, and I will start the tapering from J. Why from J this time? Because in this we are tapering it from support section. So initially 3 meters I'm having support, okay, and then from here I'm tapering it to the span section. Okay, so my tapering is basically, so this becomes my ith end and this becomes my jth end. So my tapering basically starts from j to I. So I am choosing j here. Okay, I hope it is clear. So I will just choose j here and click on modify and then click on OK. Okay, so this way I did the tapering for the deck 5 section. Okay, so deck 1 we have done, deck 5 we have done. So in deck 2, so what will be my deck 2? Again in the PowerPoint, if I show you, so we have considered up to this point. So we have done deck 1, this is our deck 5. So deck 2 will be something like this. Okay, so again we have to taper at both ends. Okay, so to consider the deck 5 section, sorry, deck 2 section, so we have to go to tapered option again, tapered section segment, and then from here, from the start, location 3 meters, I'm choosing support section, and from start only at 65 meters, I'm choosing span, okay, and at 127 meters, the total length of the deck was 130 meters. So at 127 meters means 3 meters from the support, again from the 3 meters from the pier. So up to that only we are considering tapering. So I will choose support. So I have 3 sections here. Okay, so this way it will taper. So I will choose on tapered option. So initially I will choose from from J. Okay, so I will just click on modify, and after that I will choose from I and click on modify. Okay, so this way I choose it for deck 2. Again I can just copy the current data to other decks. So I can choose deck 3 and 4 also, because it will have the same sectional information. So this way, we have to click OK after this, and so this way it is copied automatically to all the other decks. Okay, after that we have to choose the rail section. So we haven't added any rail section, so either we can add the default rail section as per UIC, so I can add a rail section like this. So now if we go to the section database, you can find the rail section. Okay, so this is automatically defined as per the UIC, or if you have your own rail section, even if you have some non-uniform section, some unconventional section, then you can directly import it from AutoCAD into Midas Civil and then use it. Okay, so we have imported, we have added one section for rail. We can choose UIC 60 here, and we can define an eccentric loading from as per our eccentricity. At present we can add only one eccentricity. Okay, but we are doing development so that we can add more eccentricities as per the rail. So we can also define the track positions. So we can define the track positions, traffic lane positions, so where exactly that my lanes will lie. So I can define here 2.5 meters, suppose from the center 2.5 meters left my first track is there, from the center 2.5 meters right my the second track is there. So I can choose like this. So in the draw you can find my rails will be something like this. Of course it won't show you the section here because we are doing a tapering section. Okay, so at the end I will be, when the model is generated, I will be showing you the sections also. Okay, this way we define our sections. So after the sections is over, we go to boundaries. So in the boundaries we need to enter, as you remember from the presentation itself, so I need to enter for for ballast bed and for the concrete bed, because we are also considering the embankment. We need to consider the ballast bed and concrete bed both, right? So in this, for the ballast bed, I'll be considering, as per UIC code, the lateral limited displacement. Similarly, for unloaded conditions, we are giving 20 kN per meter. For stress check, for displacement check, however, it is around 12. And for the loaded conditions, I am giving 60 kN per meter. Similarly, for concrete bed, I have to consider according to for the concrete bed. So it is 0.0005 as per UIC code. For the unloaded conditions, we have 40 kN per meter. And for the loaded conditions, we have 60 kN per meter. So currently only ballast bed and concrete bed both we are considering, okay? But for the conditions, when we see, we can only define ballast or concrete. So what if we are considering both the things together? So what should we do? So in that case, you can just click on the checkbox besides advanced. You can click on advanced here, and you can choose from start up to how many meters is my ballast bed. Then from 300, the total bridge length is 560 meters. So I can enter here 860 meter. This is my concrete bed. And from 860 again, at the end, 300 meters is my ballast bed. So I can enter these conditions also. Okay, so automatically the software, what it will take? It will take the ballast bed lateral resistance data and the concrete bed lateral resistance data according to the information that we have given here. Okay. Similarly, what we can do is that we can go for spring type or or bearing type data. So this is very informative in Midas Civil. If you go to guide, it will explain you each and everything very clearly. So if you go for spring type, this is the kind of situations that it will handle, Midas will handle. So it will give multilinear elastic link from the rails to the deck centroid. Okay, and wherever the supports are there in the deck, it will consider a rigid link here over the supports, and it will give the supports at the end. Okay, similarly, if we go to bearing type, we have the pier also in this case. So the pier will come at the bottom, and in between for the bearing, we can give the bearing properties or anything according to our wish, whatever the bearing properties are there. So if we are considering, suppose elastomeric bearings, in that case we can give some stiffness properties in here. Okay, so we have the flexibility to define it. For the embankment case, it will consider the multilinear elastic links like this, and it will consider the full fixed supports at the bottom. For the embankment and deck start point connection, what it does is that, because at that point for the embankment we will have the fixed connection property, I mean a fixed constraint, but for the deck portion we are having some other boundary condition. So it considers two nodes there coincident to each other having different stiffness. Okay, so it automatically does it. And similarly for the deck end and start point connection. Okay, so for each deck, according to the span information that you gave initially, that if you are giving simply supported or a continuous brace or like that, it will automatically consider the support conditions as per the information that you have given. Okay, so once you have done that, what we can do is that I am choosing the bearing type now, because I need to consider the piers also here. Okay, so I can either give directly the horizontal stiffness for each and every elastic link. Okay, I can either give like this, or I can choose advanced, and for each deck I can give separately. So both the options are there for you, available for you. So you can choose the length of bearing or whatever elastic link length that we are considering. For the pier section, I can either choose pier like this and pier material. So C4000 material I can choose. Okay, or I can go to advanced pier data. Okay, and in here I can choose material like this. So I can copy this. Second. So in here you can have different peer data for each and every options like this. Okay, so we can have different peer data also. So I can also choose 40 meters. I can also choose the height of the peers. Okay, so this way, whatever is the height of the peer, you can just directly enter in here. Sorry. Okay, so this way you can enter, or you can also select the peer at the bottom of the peer what type of support you are considering. So you are either considering a full fixed support or you are giving some spring stiffness there. So you can consider those options here also. And where exactly the peers you are considering. So you can consider the peers according to this. So we are considering 4 peers at all these positions. Okay, so this way you can enter the peer data. Okay, also you can give I can give either fixed support or spring supports, because they've given advanced, so automatically it will take fixed support at the bottom of all the peers. You can also choose shear spring location for the elastic link. Okay, in case if you want the shear checks to be done for the springs also, elastic links also, you can choose it, you can select it. After we have considered the boundary conditions, we can go to the loads tab. Okay, so this is my loads tab. So in this I can consider the deck temperature. So you can, because we have given the units as Fahrenheit, it is coming as 25 Fahrenheit, but I can change it afterwards. So currently I am just giving 25. Also the running direction I can give either left or right like this. See, keeping left means the track 1 will be traveling on in the forward direction, and track 2 will be in the train will be traveling in the backward direction. So if we consider right, it will become opposite. Okay, so we can have either left or right. See, so automatically it will change. Here we can consider the braking load. So braking load, as per the discussion in the PPT, I can give it as 4.9. Span start point, I can give it as 300 meters or something like that. Okay, so I can give it as 300 to 500 meters. So from the embankment I am starting. Similarly, vertical loading that is coming for the train will be 27.2, and this I can give it as 300, 500 again. So automatically the length will consider. There is one more option here, that is train section. This option is there, and this option is only useful. Suppose in case you are not considering any loading, you just want to check the loading stiffness in the bearings. So in that case you can give the train length. So wherever the train section you are defining, like in here if I define 300 to 500, so even though if you don't apply any loading, the software will automatically consider the loaded stiffness in the section between 300 meters to 500 meters. So the train section is useful in such cases. Also you can understand that we are giving a UDL here, right? So what to do if you want to consider a concentrated load? So in that case I can consider, suppose if I want to consider a concentrated load vertical of 100 kilonewton. So in that case I can only enter 500, 500. So automatically it will be coming as a concentrated load in the section. Okay. So similar kind of data I can enter it for the track 2. So I can enter an acceleration here. So 4.9 as we gave. Start point we can give it as 660 meters to 860. This is because one train is coming from here. One train is lying at one end of the bridge. The other train on the track 2 is coming on the other end of the deck. So what we will do is that we will shift this position on both ends like this. Okay. So again we can consider the vertical loading. So I can give a 27.2 here, 660 to 860, like this. Okay, so this way we consider both the loadings. Now we have to enter the moving load data. So what is the moving load data position we have to enter? So number of track loading locations we can enter as depending on the number of track loading locations. What it will do, I will just make you understand. Suppose if we give 4 here and we give 50 on for both track 1 and track 2, 50 meters. So what it will do is that these are my 2 rails, right? So initially my train loading is on track 1 here and track 2 on this end. So it will shift this load 50 meters ahead to give the next train loading for the track 1. And it will shift this load 50 meters this side for the next position. So how does it affect the structure? It affects the structure because initially in the first model, so this is my first model. Initially in the first model, the spring locate the multilinear springs underneath this train position were having the loaded stiffness. Okay, underneath this train position were having the loaded stiffness. But after some time, when it shifts to the new position, the multilinear link underneath this position, under the updated position, will be loaded stiffness, and the other portion of the brace will have unloaded stiffness. So the stiffness data will also change according to the loading. Okay, so the software, what it does is that according to the number of track loading locations, like 4 track loading locations we have given, so it will automatically generate 4 different models for it. Okay, with the loaded stiffness and unloaded stiffness data automatically entered. Okay, so I hope it is clear. Next in the final is wizard position. So I can choose meters here. Usually element length that we give is according to the UIC code, it is given as 1 meter. Actually it is an effective element length. So how much an element length should we give? It means that only. So based on the entered element length, the effective length of rails and the resistance of ballast in multilinear elastic link will be determined. Okay, so and next is the stress check model. So if you remember from the previous webinars, we had one simplified separate analysis model and we had one complete analysis model. So we can consider both those cases in Midas Civil. Okay, so we can have the simplified separate analysis model or complete analysis model together. Okay, so for now I will just show you the simplified analysis model. Also to check the longitudinal displacement, the relative longitudinal displacement due to acceleration and braking or due to vertical loads. Okay, so we can consider these options also if you want to consider. Okay, so I will just show, if I just click on OK now, just a second. Also one more option I want to show you is that if I go to save as, okay, so I can save this wizard file anywhere that I need. So if I have done one wizard and I want to edit that wizard option only for the next all the projects, I can save those wizards there itself. Okay, so this way I can enter all the section properties. Okay, so once we have done that, we come back to the position and then we click on OK. So it gives you some sounds relating to number of files that it has generated. Okay, so it will take some time because of the length of the bridge. Okay, so it generates the full model in front of you. Okay, so everything is generated from start to end. So you can just see yourself that and the effort of around a week or so is reduced just within 1 hour. Okay, the full deck with the embankments is generated in front of you. You can also see that this is the train moving load 4. Okay, so if I go to the folder where I saved it, so you can find out that it has automatically generated all the separate analysis files according to the number of positions that we gave. So it generated one file with only temperature, it generated one file with train, it generated one file with moving load 1 position, then moving load 2 position, then moving load 3rd position. So it can generate all those positions. It generated files for all those positions. So if I just show you one by one, how does it look? So I've already done all these things. So I will just show you. So this is just simple train loading file. Okay, so in train loading file, you will only find train loads. So this was the initial position we defined, if you remember. Okay, so from this, these are 2 tracks. Okay, just a second. So it is something. So these are the 2 tracks. On both the tracks, the train loading is applied. Okay, this way. This is a top view. So if you go closely, you will find that the rails are at the top of the section. Okay, so if I just undisplay it and go back to the solid view, okay, so if I go to the solid view, you can see the rail section that is coming. So this is the rail section that is coming. Okay, it will be a little lag, and there will be some little lag in between the screens that is coming to you because of the nature of the file. Okay, so please bear with that. And also, if we see the elastic links, so these are the elastic links. So if you remember, we give the multilinear elastic link. Okay, so this way the multilinear elastic links are considered. Okay, so the rigid link is considered here, and the bearings. If you remember, we gave the bearing properties. Okay. Also, if I want to check under train loading, what is the elastic link properties that I have given? So I can right click here, go to the tables. So in here we are giving the elastic link properties. This is the elastic link properties generally we have given. Okay, and for the multilinear elastic link, I can go to this option. Okay, so the multilinear elastic link is there. So what we can see from here is that wherever the train loading is there, see the positions wherever the train loading is there, you can easily find out that it has taken 60 kilonewton as the, so because we have considered the effective length as 1 meter, so it has taken a 60 kilonewton as the resistance offered by the multilinear elastic link. Similarly, wherever the ballast bed is there for unloaded conditions, it has taken 20 kilonewton resistance. Okay, so these all things, just imagine if you have to input it manually, how much time it will take, because it has generated so many elastic links. Okay, and also it has automatically changed the unloaded and loaded stiffness according to the loading that is there. Okay. Similarly, for the piers, if we consider the piers, if you remember, we gave a tapering only up to the 3 meters from. Yes, if I go to the front view, it will be more easily visible. I will just sun display or something like this. So if I magnify and show you, if you remember, we did the tapering from both ends. We kept for 3 meters. We kept the support section only. So in here also, this is around 6 meters because we gave the elastic link length as 0.2 meters. So automatically it takes 0.2 meters here in between the pier and the section, and it gives the elastic link properties here. You can also manually change these properties. So it doesn't mean that by Wizard, because we have generated the full model, we cannot change it. You can also change this model change the modeling features, all these features like elastic link features. So you can change it by going to elastic link tables, and you can change the properties here like this. Okay, so if you go to the elastic link properties, second. Just a second. So you can change all these properties according to your will. So for the bearing properties also, you can find what elastic link is there. So between nodes, you can just check in what nodes is there. 3492 and 3501. So you can go to the elastic link, respective elastic link. You can also display the number of elastic link. So it depends upon the user on what number he is using. Okay. Just a second, I will just check the. Okay, so this way you can just check. You can go to general. You can define your own elastic link properties here. Okay, so this way you can change the elastic link properties also. Okay, similarly for all the train positions, this is moving load 1. So after the train, after the first iteration, the model that is generated, you can just find the train load here now. It will be much easily visible if I do this. Just a second. So it has shifted 50 meters from both ends in both directions. Okay. So as you can find in here, okay, so similarly if we go to the next model, okay, so it generates all the model files, so you can open all the models and you can find out the train loading positions for each and every model. So in the next model it shifts a little more ahead. So this way it considers all the things together. Currently what you have to do is that you have to extract the results for all these positions into Excel sheet and then create an envelope for all these cases to find the most critical result. Okay, but we are working towards it. So what we were working towards is that it automatically generates the envelope on its own. Okay, so after we have done the analysis, so we can, what we can do is that we can check the results for each and every positions. So for each and we can also do a batch analysis. For analysis, if you want to do a batch analysis, so you can add all the loading positions, all the files that is there. Okay, so you can consider all these files together and do an analysis of all these files at one single time. So you can do a batch analysis to get all the results together. I mean, all the files will automatically analyze on its own. Okay, and then you can find the results for each and every file. So you can go to stresses, beam stress diagram, okay, to find the stresses related to the rails. So since we are interested in the axial stresses related to the rails, so we can just plot a contour of the axial stresses. Okay, so this way I can just check the results. If we go to Newton millimeters second, so we are getting an axial stress of around 27.8 kilonewton that is in the positive side, and the negative side we are getting the axial stress as 73 kilonewton per meter square. That is 73 Newton per millimeter square, that is 73.4 pascals. Okay. Similarly, we can check for the other loading positions also. This is from the just okay. For this also we can check. So again we can go to stresses, beam stress diagram. Okay. For vertical loading or braking or acceleration loading. So I can check again, apply. So this is for another position of rail. Okay, so this way we can see the results here. Okay, so this is the graphical display. But sometimes what we need is that we need to export these results into Excel. So for that case, I can go to result tables. Okay, and beam stress. So I can choose train or vertical loading like this. Okay, but if you want to choose only rails, for only rails, what we can do is that whenever the model is created by the wizard, it automatically creates some groups. Okay, so it automatically creates, if you see here, it automatically created for displacement deck 1, it automatically created the displacement deck 2, deck 3 group, deck 4 group, deck 5 group. So it automatically does it. So if I consider, suppose only the tracks, both the tracks if I consider, or for track 1 or track 2 I consider. Okay, so I can just copy all these elements. Okay, so all these elements that are there, so what I did, I just double click on the group, I found out what elements are there, I copied all those elements. Okay, and I went to track, I pasted it here. Okay, so I just want the at part I, suppose the stresses, so it automatically gives you the full stress information, axial stresses, shear stresses and everything. You can directly right click here and go and choose export to Excel. So automatically this table will be exported to Excel. Okay, so this way you can export to Excel all these files. Also, sometimes what we want to see is that, okay, I will just show you the Excel results. Okay, so this way you can just export it to Excel. Second. So it shows you the beam stresses here. Okay, so all the things, all the results are exported to Excel. So in this way, you can also see the bending moment and stress diagram and everything for rails and deck and compare both the things. Okay, so what you can do is that you can, or displacement due to in rails and deck. Okay, so how you can do is that you can go to results and choose diagram. Okay, and then you can choose define diagram dx. From the elements you can choose track 1 and track 2 for rails. Suppose I'm choosing only track 1 here. Okay, so I can type in here dx for rails. Okay, similarly we can add for the decks. So automatically the elements, the list of elements comes. Okay, and I can write in a dx deck and then click on add. After that I can just click on plot diagram for both cases. The second, so I can choose different colors. Okay, so this is how you can choose a plot for displacement for both deck and rail. Also for temperature stresses, we have found the analysis results for this is for the train loading, right? For temperature, how to find the results? So for temperature load, again it generates a separate file for temperature load. So I can just right click here, go to stresses, beam diagrams. Okay, another thing is that, yeah, just a second. S6 again, legend, apply. So these are the results for temperature. So it comes around 42.3 MPa. Okay, so this way you can check the results for temperature also. You can again find the displacement for the temperature, displacement in rails. So for that case, again you can go to results, result tables. Okay, you can go to displacement directly. So we need to consider, if we want to consider the displacement in a deck due to temperature, what we can do is that, just a second, I can again go to group, choose all the deck options. So we get 1 to 560 here, copy it, go to activate records, okay, paste it in here, we get a displacement. So we'll just go to millimeters because the displacement is very less due to temperature. Okay, we can also plot a graph directly in here, show graph. So this way we can plot a graph also for temperature analysis. Okay, this is these all things are basically related to separate analysis. Okay, but in case we do a complete analysis instead of separate analysis, so I have done one file using complete analysis. So I will show you what it does in complete analysis. So once we have done the complete analysis, if we go to so again it generates all the complete analysis plus the movie load. For all the movie load position it generates the files. Okay, so once we have opened the complete analysis model, this is a complete analysis model. So you find here that we have actually defined two stages. Okay, So it defines, the software will automatically define two stages. One is the unloaded stage and one is the loaded stage. Okay, so these are the two stages that the program will automatically consider. So in the unloaded stage, if we go to the construction stage, it only includes the temperature load here, and in the loaded stage, it includes the train load. Okay, so train load will automatically consider the vertical and the braking loads. So this way we can consider both the, this is the complete analysis, means it is a staged analysis. So this gives a more practical solution. Although it will give you lesser values than the separate analysis, but it will give you a more practical solution. So here you can find where the trains are. So there are the train positions. Okay, so automatically if I go to forces, again stresses, beam stress diagram for the unloaded stage, axial stress. If you want to consider the bending stress also, then we can choose combined. So combined will include both the axial stresses and the bending stresses. But if you want to choose only axial stress, we can see the values from here. So this is for axial stress. So it is nearly equal, that is 42.3 MPa, similar to that of separate. And when we go to the loaded stage, okay, so we get around 77, 54 MPa. This is for the loaded stage. So this is a more accurate analysis, okay, for the rail section interaction. So this is in all about modeling and everything. That I have discussed is how to create the full bridge in just a few minutes. The full bridge is constructed is modeled within 1 hour, as you have found out yourself. Okay. After this, if I come back to the presentation, we come to the conclusion of today's webinar. I'll be taking up all the question answers at the end of the webinar, so please don't worry about it. Okay. So for the conclusion, to conclude the full webinar series, what we have learned through this webinar is that we have considered, we discussed some advanced technologies related to metro bridges and engineering. Okay. So we discussed some of the features of Midas Civil which we can use effectively for metro bridges. Also we learned about rail structure interaction, what is RSI, okay, and why is it needed, how can it be effectively used, okay, case studies, major case studies reflecting the advent of RSI, okay, live modeling of complete bridges with rail structure interaction. Okay, so we covered all these topics for rail structure interaction, and we also covered some effective measures in Midas Civil to handle such RSI problems and metro bridges, like balance cantilever. Also we discussed balance cantilever, we discussed integral bridges. Okay, so this in a way it gives you a complete picture of metro rails. Okay. So upcoming webinars, like we have one geotechnical webinar also somewhat related to metros, because for geotechnical engineers they are also interested in tunneling. So we have one webinar that is coming, that will be done on 21st June 2014. It will be organized by Akash Sharma, technical engineer from Midas IT. So there he will be considering the tunneling portion. So that I think will be useful for you in case you are interested in the geotechnical field also. So it will be discussing the terrain geometry maker, the TBM analysis and everything in that webinar. Also, just to close the webinar, just to close this series, We have some special proposal and technical support for special promotional offers for this series. So we have one Midas Civil Advanced version plus Rail Track Analysis module. Just to inform you, Rail Track Analysis module doesn't come with the Midas Civil. It has to be, it is a separate module. So we are giving some discounted price or something in some discounted price. Similarly, we are giving some free rental service for metro rail projects. We are also considering to organize some metro rail online training service. Okay, so we'll consider this. We'll do a special course for Rail 6 interaction on July. And finally, you can have all the training DVD material also. So whatever training DVD material that we have, if you want a copy of it, we can give that training DVD material. So finally, to end this webinar, if you have any queries and any doubts, you can always mail us to techsupport@midascity.com. And I hope that you like the webinar series, and you're always welcome to post you're always welcome to mail your reviews about the webinars, so that we can conduct it in a more proper way, in a more organized way in the next while we are doing it next time. Okay, so thank you for joining this webinar, and please join the upcoming webinars. Yes, after this webinar we are taking the question answers also. Okay, so this ends the webinar now.